First, let us define radicals. Radicals are about nth root of a number. Suppose we have a variable b raised to an exponent n, and this is equal to a value a. Then the b, this b here, is an nth root of a. As an example, we have 5 squared equals 25. So this number 5 is the square root of 25. The principal nth root of a is written as, the symbol read as nth root of a. On the general form, radicals will come like this. The small number n is called the index, the a is called the radicand, and this symbol like a box, like a division box, is the radical sign. We have some notes here. The symbol like this is read as square root of x, and the index is 2. Another, the symbol like this is read as cube root of x. Obviously, the index is 3. Now we have some examples of widely used radicals. We have square root of 1 is equal to 1, square root of 4 equals 2, square root of 9 equals 3, square root of 16 equals 4, square root of 25 equals 5, square root of 0 equals 0, square root of 100 equals 10, cube root of 1 equals 1, cube root of 8 equals 2, cube root of 27 equals 3, cube root of 64 equals 4, cube root of 125 equals 5. Those numbers inside the radical sign are called perfect square or perfect cube numbers. The numbers 1, 4, 9, 16, 25, 0, 100, these are perfect square numbers. While the numbers 1, 8, 27, 64, and 125 are examples of perfect cube numbers. Let us go to the relationship of radical and rational exponent. If we have a radical nth root of x, and this is a real number, and the n is greater or equal to 2, take note that n is the index. Then, the relationship of radical and rational exponent is given in this equation. So the nth root of x equals x raised to a rational exponent. So we have a note here, the index, the n, of the radical becomes the denominator of the rational exponent. Next, the radicand, the x, becomes the base of the rational exponent. Let's go to some examples. We will convert radical to rational exponent. So write the following as rational exponent. We have 3 sample problems here. The first one, square root of 5. Second is the cube root of y. The third is the fourth root of the quantity x minus 2. So I put the equation here for the conversion. Let us now solve the first sample problem. The square root of 5 becomes 5 raised to the exponent 1 over 2. So we simply write the radicand, put it as the base, and then in the exponent we write the number 1 over the denominator, we will simply copy the index of our radical. In this case, there is no number. And if there is no number, it is understood to be 2. So the square root of 5, there is an index of 2. So with that 2, we will use as denominator. So the final answer here is 5 raised to 1 over 2. Second example, the cube root of y becomes y raised to 1 over 3. Again, we see the index 3 there becomes the denominator of the fractional exponent. Again, our final answer, y raised to 1 over 3. Third example, the fourth root of the quantity x minus 2. First, we will copy the x minus 2, and then we will write the fractional exponent. So we write the 1 as the numerator over the index here, the 4, we copy that as the denominator here. So 1 over 4. Our final answer, x minus 2, all raised to the exponent 1 over 4. Let us go to the reverse process. Let us convert rational exponent to radical. So express the following as radical. We have 3 sample problems here. First one, the quantity x plus 1 all raised to the exponent 1 over 2. Second example, the quantity 5y is raised to 2/3. Number 3, the fraction 3a over 4b is raised to 3 over 2 exponent. So let's begin with our first example. Now this x plus 1 is the base. We will put all this polynomial into the radical symbol like this, and then for the index we will copy the denominator. In this example, our denominator is 2. So for this, we don't need to write the number 2 here. So this square root of the quantity x plus 1 is our final answer. So for the second example, the 5y is the base. We will put the base inside the radical sign, the 5y. We will check the denominator of the exponent, that is 3. We will put that as the index here. And then the numerator 2 becomes a power. So you see here 5y is raised to power 2. And from here we can simplify our radicand. We can distribute the exponent 2 to the 5 and the y. So it becomes 25y squared. So the final answer is the cube root of 25y squared. Sample number 3, our fraction 3a over 4b. We will copy all this, put it inside the radical sign, like this. Next, we will check our denominator. It is 2. So we will put this 2 as index. Since it is 2, there's no need to write our index because it is understood without any index, it is 2. Next is the numerator 3. We will use this numerator as the power of our fraction. So you see here the 3a over 4b is now raised to a power 3 inside that radical sign. And then the exponent 3 we can distribute to the terms of the fraction. So for the final answer, the 3a cubed becomes 27a cubed all over. The 4b cubed becomes 64b cubed. We're going to study properties of radicals. First, let us review the general form of radical, and this is the nth root of a. We know that the small n is called the index. and the term inside the radical sign is called radicand. And this is our radical sign. Now let's go to properties of radicals. First one is, for a real number a, when n is odd, the radical nth root of a is always real number. Take note, the n there is the index. Let's have example. Cube root of 20. So the number 20, our radicand, is a real number. Our index is an odd number, it is 3. So this cube root of 20 is a real number. Another example is the 7th root of negative 8. First, we know that the negative 8 is a real number, and the index 7 is an odd. So this 7th root of negative 8 is a real number. Let's have the second, when n is even. First, the nth root of a is real if a is greater or equal to 0. It means the radicand a can be 0 or greater than 0. Another case is this nth root of a is not a real number if a or the radicand is less than 0. In other words, the radicand is negative. Let us have example. The square root of 11. So 11 is a real number. In here, our index is 2. So the square root of 11 is a real number. Another example is the 4th root of negative 100. Obviously, our index is 4. It is an even number. Our radicand is a negative number. So in this case, the 4th root of negative 100 is not a real number. Let's have property number 2. Letter A, when n is odd, or when the index is odd, when we have this expression, the nth root of a raised to n power, it is equal to a. Take note that the index n is equal to the power of a, which is also n. And this is the simplified answer for that. We will take only that value a here. Let's have example. The 5th root of 4 raised to 5. So this is equal to 4. It seems like we are cancelling the radical with that index 5 and also the power 5. Another example, the cube root of negative 6, and that is cube. So the answer here is negative 6. What about when n is even? So this is the nth root of a raised to n is equal to the absolute value of a. Take note, we will use the absolute value sign when taking an even root of an expression with a variable in the radical. Example, the 4th root of 10 raised to 4. So this is equal to 10. Another example, in here our index is 8 and it is even, and our radicand is raised to 8 power. In here our answer is 7, positive. Another example is square root of x raised to 6. we can show this to be the square root of x cubed, that is squared. So in here our index is 2, and there is a power 2 here, and our radicand is the x cubed. So it seems we can cancel the radical sign with that index 2 and the power 2 here. But when we simplify, we will show the absolute value of the x cubed. Let's have the property number 3, simplified radical expression. For a real numbers a and m and an integer n greater or equal to 2. So take note, our a will be used as radicand, the m will be used as a factor of this a, and the n is the index. The nth root of a is considered simplified if a has no factors of the form m raised to n. So a here is our radicand, and the m is a factor of a, but take note, the power of m here is n, and this n is the same index of our radical. So another notes here that this m raised to n is a perfect n factor of a. Another consideration is the m or the base here should be greater or equal to 2. Let's have an example. The square root of 24 is not simplified because 24 has a perfect square factor of 4. So we can still simplify this square root of 24 by simply showing that this 24 has factors of 4 and 6. And the 4, we can show that it is equal to 2 square. And then we can split the radical into these two factors. The square root of 2 square is separated from the square root of 6, and then we show the multiplication symbol. And this expression here, the square root of 2 square, we can simply cancel the radical sign and the power, and then we use the 2 and connected with the square root of 6. So it means the square root of 24 is equal to the value 2 square root of 6. Another example is square root of 10. The square root of 10 is simplified already because there are no perfect square factors in 10. So take note, the square root of 10, our index here is 2. So we are looking for a perfect square factors. Unfortunately, there are no perfect square factors for 10. So this expression is already simplified. Define simplified radical expressions. A radical expression is considered simplified if there is, number 1, no factor in the radicand having perfect powers of the index. Example here is square root of 20. This radical is not simplified because the 20 has a factor of 4 and 5. And this 4 is a perfect square number. The index is 2, so there must be no perfect square number inside the radical. So we're going to simplify this by simply putting this 4 outside the radical sign, so it becomes 2, and then the square root of 5. The second, a radical expression is considered simplified if there is no fraction in the radicand. Let's have example, the square root of the fraction 6 over 3. So when we divide the 6 by 3, so we'll get this square root of 2. So this is now the simplified form. A radical expression is considered simplified if there is no radical in the denominator. Example is 3 over the square root of 6x. Today we're going to study simplification using product property of radicals. Let us define product property of radicals. Suppose there are two radicals here, the nth root of A and the nth root of B, and these two radicals are real numbers. And the n, and that is the index, is greater or equal to 2, and the index is an integer. Then, if we're going to multiply this nth root of A and the nth root of B, take note that the index are the same. The answer will be that radical with the same index, and we're going to multiply the A and the B. So you see here, the answer is the nth root of AB. This equation here is what we call the product property of radicals. On the other hand, suppose I have a radical here, which is the nth root of a product AB. I can now split the radical into each of the factors, and we shall see here this is equal to the nth root of A times the nth root of B. It's like the reverse of this multiplication or product property of radicals. And this idea here is what we call the simplification rule. Let us see some examples. Example 1, let us simplify square root of 500. So I put the formula here for the simplification rule. The idea is we're going to factor out the radicand or this number in such a way that one factor must be a perfect n number. Our index here is 2, so we're going to find a perfect square factor for this 500. So we have here the square root of the product 100 times 5. And this 100 is a perfect square number. So we're going to apply now our simplification rule. We're going to split the radical into each of the factors. As we see here, we have the square root of 100 times the square root of 5. Then we shall show that this 100 is equal to 10 square. The next step, we're going to cancel the radical and the power 2. So the 10, the radicand itself will come down without the radical and also without the power 2, and then times the square root of 5. So in here, we just simply combine the two numbers, the 10 and the square root of 5, and this is our final answer. Let's have example 2. The cube root of 24x raised to 7. For the numerical coefficient, we will factor out this 24 in such a way that one factor must be a perfect n number. For the variable whose exponent is greater than the index, so in here our exponent of the variable is 7 and our index is 3. So the 7, the exponent, is greater than the index. We're going to factor out this variable in such a way that one factor has exponent with highest multiple of n, highest multiple of the index. So as we see here, the number 24 is factored out into 8 times 3, and this 8 is our perfect cube number. Take note that our index here is 3. For the x raised to 7, we factor it out into x raised to 6 times the x. So the power 6 here is the highest multiple of the index 3. Next, we're going to split the radical into each factors of our radicand. So we have now the cube root of 8 times the cube root of 3 times the cube root of x raised to 6 times the cube root of x. And then we're going to show this number 8 to be equal to 2 cubed. This one we'll just simply copy down here, and this term here, the x raised to 6, we're going to show that this is x squared and raised to power 3. And the cube root of x we simply copy here. The next step is, for this term we're going to cancel the radical with that index 3, also the power 3. The number 2 will come down. For the cube root of 3, we'll just simply copy here. For this term, we're going to cancel the radical also with the index 3, also with this exponent 3. So only the x squared will come down. The cube root of x will just copy down here. And then we're going to multiply all terms without radicals and all radicals together. So we have this 2 multiplied to x squared, we have 2x squared, the cube root of 3 multiplied to the cube root of x, so it will be the cube root of 3x. So this is our final answer. Let's have example 3. Let us simplify the square root of 63 x raised to 7 y z squared. As per our rule, for the numerical coefficient, we're going to factor out such that at least one factor must be a perfect n number. So our index here is 2, so we're looking for a perfect square factor for this 63. And for the variables with exponent greater than the index, in here only the x has the exponent greater than the index. So we're going to factor x in such a way one factor has an exponent that is the highest multiple for the n, highest multiple for the index, and that is 2. So what will happen is, for the 63, we are going to have the factors 9 times 7. So the 9 is our perfect square factor. For the x raised to 7, we're going to factor it out into x raised to 6 times x. So this 6 here, exponent, is the highest multiple of the index 2. For the y, the exponent is 1, we'll just simply copy. For z squared, the exponent and the index here are equal, so we'll just copy that. There's no change. And then we're going to distribute now this radical sign to each term inside this big radical. So we have now the square root of 9 times the square root of 7 times the square root of x raised to 6 times the square root of x times the square root of y times the square root of z squared. Then we will show that this square root of 9 is equal to 3 squared. Now look at this square root of x raised to 6. We're going to show that this is equal to x cubed and again raised to 2. Cancel the radical now and the power 2. So the number 3 will come down. The square root of 7 will just copy. In here we will also cancel the radical sign and also the power 2. So x cubed will come down. The square root of x will just copy. The square root of y will also copy. And for the last term, the square root is cancelled along with the exponent 2. Only the z will come down. In the next line, we're going to multiply all terms without radical and all terms with radical. So we have now the 3 multiplied by x cubed times the z. Here it is now 3x cubed z. And then for the radicals, we have the 7 times x times y are all inside the radical symbol. So our final answer is here, 3x cubed z, square root of 7 xy. Today we're going to study simplification using quotient property. First, let us define this quotient property of radicals. Suppose there are two radicals, the nth root of a and the nth root of b. Take note that the index are the same. And these two radicals are real numbers. Another condition is the b, which is the radicand of the second radical here, should not be equal to 0, or else this radical will be equal to 0. So that's why it is given the b should not be equal to 0. And for any integer n, and that n is the index, should be greater or equal to 2. Then, we are going to divide the nth root of a by the nth root of b. The answer is a big radical with the index n. Inside the radical is a fraction, whereas the numerator is a and the denominator is b. So this equation here is what we call the quotient property of radicals. Suppose I have a big radical here with an index n, and inside the radical is a fraction a over b. To simplify this using the quotient property, we're going to distribute the radical to the a and to the b respectively. As you see, this is now equal to the nth root of a over the nth root of b. This is actually now called the simplification rule based on that quotient property of radicals. If you notice, this equation here is also that quotient property, but the position of the left side and the right side members are interchanged. Now let us simplify a radical expression using the quotient property. We're going to follow some steps. In step 1, we're going to simplify the fraction in the radicand, if possible. Step 2, use the quotient property to rewrite the radical as the quotient of two radicals. Step 3, simplify the radicals in the numerator and the denominator. Let's have some examples. Let us consider this example 1. Simplify the cube root of the fraction 32 over 54. In step 1, we need to simplify the fraction in the radicand, or simply we need to reduce the fraction to lowest term. You see the 32 is factored out into 2 times 16, and the 54 is factored out into 2 times 27. And then the number 2 in the numerator and in the denominator is there. It's common that we can cancel. So now the radical is simplified into cube root of 16 over 27. We will now go to the step 2 where we're going to use the quotient property. It means we're going to distribute this radical sign to the numerator and in the denominator. So we have the cube root of 16 and then the cube root of 27 in the denominator. We're going to check the radicand of each of the numerator and denominator if they are in the form of a perfect n number. Since our index is 3, we will check if the numbers are a perfect cube number. In the numerator, 16 is not a perfect cube number. In the denominator, 27 is a perfect cube number. So what we'll do now, in the numerator, we're going to think of factors of this 16 such that one of the factors is a perfect cube number. In the denominator, we're going to show this 27 to be 3 cube. And then, in the numerator, this number 8, we can show it to be 2 cube. And then the other factor, 2, will be copied down here. In the denominator, we simply copy again that same value. Now, in the numerator, we're going to apply simplification using product property. It means we're going to split the radical into each of the factors. You see here we have the cube root of 2 cube times the cube root of 2. Then in the denominator, we can now simplify by cancelling the radical and also that power 3. So only the base 3 will come down here. In simplifying this first term here, we're now to cancel the radical and also the power of 3. Only the base 2 will come down, and then multiplied by this cube root of 2 all over the denominator 3. So this is our final answer. Let's have example 2. Let us simplify the fourth root of the fraction a raised to 10 over a square. In step 1, we need to simplify the fraction in the radicand. So we have here exponent with the same base. We can apply our rule that it is equal to the a raised to the 10 minus 2. And then the big square root is outside with the index 4. So it is now simplified into the fourth root of a raised to 8. Step 2 can now be omitted because there is no more fraction inside our radical. So in step 3, our index here is 4. So we're going to show that this a raised to 8 is a power of 4. The term inside here is a square. So now we can cancel the radical with that index 4 along with that power 4. And the answer is this a square with the absolute value symbol. That exponent 2 will make the value always positive, so we can simply delete that absolute value symbol. So the final answer is a square. Let's have example 3. Let us simplify this big radical, and inside is a fraction. The numerator is 18, p raised to 5, q raised to 7, all over 32p q square. In step 1, we need to simplify the fraction. In here, we're going to group the numbers. We're going to group the variable p. We're going to group the variable q. So for the numbers, we're going to reduce to lowest term. So the 18 is now factored out into 2 times 9. The 32 is factored out into 2 times 16. As we can see, the factor 2 is common. Later on, we can cancel that. For the p, there is an exponent of 5 in the numerator. There is p in the denominator with exponent 1. So we can show that this is p raised to the difference of 5 minus 1. And for the q, we have in here q raised to 7 in the numerator. We have q squared in the denominator. So we can combine them by putting q raised to the difference of 7 minus 2. For the numbers, we can now cancel the 2 and 2. Only the 9 over 16 will come here. For the p, 5 minus 1 will be 4, so p power 4. For the q, the 7 minus 2 power will be 5, so q raised to 5. And from here, we're going to combine the 9, the p raised to 4, and the q raised to 5 in the numerator. So on this line, we have the square root of this fraction. Numerator is 9p raised to 4, q raised to 5, all over 16. We are now in step 2, where we're going to apply the quotient property. It means we're going to distribute this radical sign to the numerator and to the denominator. The next is, in the numerator, we're going to distribute the radical to each of the factors here. So you see we have the square root of 9 times the square root of p raised to 4 times the square root of q raised to 5 all over 4. So this is now the square root of 16 is now simplified into the number 4. The next is, we're going to simplify further the numerator. The square root of 9 can now be simplified into number 3. This value p raised to 4 can be represented by p squared and again squared. This q raised to 5 now can be factored out into q raised to 4 times q. So we put here q raised to 4 because our index is 2. We're going to put one factor with the exponent that is the highest multiple for the index. So this is q raised to 4 times q. The next is that q raised to 4 we're going to represent by q squared and then squared. And then this times q, just copy. Next, we're going to split now the radical to the factors. Actually, that is simplification by product property. We have now here the square root of this q squared and then squared times the square root of q. The next is we're going to cancel now some terms that can be cancelled. So in this answer, the 3 we copied here. For the second term, we cancel the radical with the power 2. And then only the p squared will come here in the final answer. We cancel the radical, also that power 2. Only the q squared will come here. Next is this square root of q we include in the numerator. And then all over 4. So this is our final answer. Today we're going to study addition and subtraction of radicals. First, let us define like radicals. Like radicals are radical expressions with the same index and the same radicand. Example, 5 cube root of 7 and 4 cube root of 7. So we see here the radicands are both 7 and the indices are both 3. So these two radicals here are like radicals. Take note, we don't care about the numerical coefficients. Let's go now to addition and subtraction of radicals. As a rule, in adding or subtracting like radicals, add or subtract the numerical coefficients and copy the same radical. In symbol, we have the a nth root of x plus or minus b nth root of x. The answer here is the a plus or minus b, and then we affix the common radical, the nth root of x. Take note that when radicals are not like, it cannot be combined. Let's have example 1. The 5 cube root of 7 plus 4 cube root of 7. Let us check the radicand and the index. So the radicands are both 7 and the indices are both 3. So these two are like radicals. So we can now add the numerical coefficients 5 plus 4, and then the common radical is affixed here. Next, we're going to simplify now the 5 plus 4, it becomes 9 cube root of 7. So this is our final answer. Let's have the second example. Square root of 20 plus 3 square root of 5. We can see here that the radicands are not same. In here the radicand is 20, here the radical is 5, although the indices are both 2. Still, these radicals are not like. What we will do is to simplify the radical if possible. It means in the first radical here, we're going to remove a perfect n square factor. Then later on the simplified form, we will check again if this radical square root of 20 becomes like with the other radical. Now the 20 is now factored out into 4 times 5. So one factor is a perfect square, and that is the 4. And then we just copy the plus 3 square root of 5 here. Then we're going to show that this 4, the perfect square number, is equal to 2 square. Then we're going to distribute the radical sign to the 2 square and also to the 5. So we have here the square root of 2 square times the square root of 5, and then the plus 3 square root of 5 is copied down here. Next, we are going to cancel the radical sign and the power 2. Only the number 2 comes down here to be multiplied to this square root of 5. Then we'll just copy this 3 square root of 5 down here. Now we were able to simplify this square root of 20. Now becomes 2 square root of 5. So we can see that they are like terms now. It means we can now apply our rule in addition of like radicals. So we will add the numerical coefficients 2 plus the 3. Then we copy the common radical, the square root of 5. So simplifying further, the 2 plus 3 becomes 5. And then this square root of 5 is affixed again. So this is our final answer, 5 square root of 5. Example 3, the square root of 32x raised to 7 minus the square root of 50x cubed. Obviously, our radicals are not like. The radicands are not the same. So what we'll do is to simplify both radicals. We're going to factor out the radicands of each of these radicals. So we will be guided by this principle. For the number, one factor must be a perfect square. Since our index here is 2, so we're looking for a factor that is a perfect square. It means, in other problem, if your index is a cube root, you must look for a perfect cube factor. In the first radical, the number 32 is factored out into 16 and 2. For the variable x raised to 7, there is a clue here how to factor out that variable. It says one factor must have exponent of highest multiple of the index. Our index is 2. So the factors for x raised to 7 are x raised to 6 and x. For the second radical, the 50 is factored out into 25 and 2. We know that 25 is a perfect square number. For the x cube, factors will be x square and x. And then we're going to show that this 16 is the same with 4 square. Then I copy the 2 here. For the x raised to 6, I'm going to represent this to be a value with power 2 because our index here is 2, but the value inside here must be x cubed. So checking here, if I multiply the 3 and the 2 powers, I will get back to that power 6. And then the x factor will just be copied down here. On the second radical, the 25 is now represented into 5 square, and the rest we just copy down here. The next line is we're going to distribute the radical sign to each of the factors inside the radical. In the first big radical, we have now this square root of 4 square, and then times the square root of 2 times the square root of the square of this x cube times the square root of x. For the second radical, we have the square root of 5 square times the square root of 2 times the square root of x square times the square root of x. And then we're going to simplify further. In this first term here, I'm going to cancel the radical and the power 2. So you see, only the base form will come down here. The square root of 2, there is no change. I will copy here. For this expression, I will cancel the radical sign along with the power 2. Only x cubed will come down. For the square root of x, there is no change. Then minus. For the second group, for the first term, I'm going to cancel the radical sign with the power 2. Only the base 5 will come down. The square root of 2, we just copy down here. For this expression, I'm going to cancel the radical along with the power 2. Only the x comes down. And the square root of x, there is no change. I will copy down here. So the next step is we're going to multiply all terms with no radicals, and we will multiply terms with radicals. So the 4 will be multiplied to the x cubed, the square root of 2 times the square root of x. So we will have this 4x cubed square root of 2x, and then minus 5 times x will be 5x, and then the square root of 2 times the square root of x will be square root of 2x. Now on this line, we can now observe that we have like radical. It means we can now apply our rule of subtraction of like radicals. So we're going to add the coefficients of the radicals. In the first group, we have the 4x cubed as the coefficient, and then minus. In the second group, the coefficient of the radical is 5x. So we'll now put them together, the 4x cubed, and then minus the 5x. Then we will copy the radical, the square root of 2x. We cannot combine this 4x cubed minus 5x because they are not like terms. So we'll just keep it as it is. So this expression, the quantity 4x cubed minus 5x times the radical square root of 2x is the final answer. Today we're going to study multiplication of radicals. First, let us have the product property of radicals. Suppose there are two radicals here, the nth root of A and the nth root of B. Take note that the index are the same. And n, and that is the index, is greater or equal to 2. And the index is also an integer. Then, if we multiply the nth root of A by the nth root of B, the answer will be the radical with the same n index with the product of A and the B. So you see here, the answer is the nth root of AB. This equation here is what we call the product property of radicals. Let us apply that principle for some examples. Let's have this example 1. Find the product of the cube root of 6 and the cube root of 2. The formula is here. As per the requirement, the index must be same. As you can see in this problem, the index are same and equal to 3. So what we'll do is simply take the radicands, the 6 and the 2, multiply them together, and the final answer is cube root of 12. Let's have example 2. Let us find the product of the first term 10 square root of 6 p cubed times 4 the square root of 3p. I put the formula here on this side, and there is a rule. We will multiply the numerical coefficients and multiply the radicals respectively. So in here I multiply the 10 and the 4, and that is 40. And for the radicals, I must check first if the index are same. So both are square root, so we have the same index of 2. So we are to multiply now the radicands. So the 6 is multiplied to the 3 becomes 18. The p cubed times the p equals p raised to 4. So this is our answer. But I observe our radical here can still be simplified. So what we'll do, we're going to factor out 18 into two numbers such that one must be a perfect square. So that is 9 times 2. The number 9 is the perfect square number. For the p raised to 4, we're going to show that this is p squared and again squared. After that, we're going to distribute the radical to each of the terms inside the radical symbol. So we have now, first the 40 I copied here, times the square root of 9, times the square root of 2, times the square root of that p squared and again squared. The next is we will show that 9 to be a 3 square value. And then we are now to simplify further. I copy first the 40. On this term, I cancel the radical along with that power 2. So only the base 3 will come down. For the square root of 2, we simply copy here. For this term, we cancel the radical along with that power 2. So only the base p square will come down here. So on this point, we're going to combine all terms that are not inside the radical symbol. So this 40 will multiply to 3, also multiply to the p square. So it becomes 120 p square, and also the square root of 2 will be copied here. So this is our final answer. Let's have example 3. There are two binomials with radicals that we will multiply. The first group is 3 square root of 2 minus the square root of 5. The second binomial, the square root of 2 plus 4 square root of 5. As per the rule, we will multiply each term of the multiplicand to each term of the multiplier. So the first group is the multiplicand, the second group is the multiplier. So if I'm going to take the first term, I'm going to multiply this to the two terms of the other group. After that, I will take this second term of the first group, then multiply to all the terms of the second group. So let's start with the first term. The 3 square root of 2 is multiplied to this square root of 2. We will get this 3 square root of 4. Next, the 3 square root of 2 times 4 square root of 5. We will get this 12 square root of 10. Now for the second term, I will multiply this negative square root of 5 to square root of 2. I will get this negative square root of 10. The negative square root of 5 times 4 square root of 5 will have this negative 4 square root of 25. Then let us simplify the first term. The square root of 4 will be 2. Later on, we will multiply to the 3. So the second term we copy also here. The third term also. For the fourth term, we can simplify this square root of 25 to be 5. Then later on, we will multiply to the number 4. On the next line, now is the product. The 3 times 2 is now showing as 6. Then for these two terms, they are like terms. They have the same radicals, same index, and also same radicand. So we can combine them. We will only combine the numerical coefficient. So this is positive 12 and this is negative 1. So it becomes positive 11. And then copy the same radical, square root of 10. Then minus the product of 4 times 5 is 20. And in here we can combine the 6 and the negative 20 to be negative 14. Then we will copy this radical down here, plus 11 square root of 10. So this is our final answer. Let's have example 4. This is now the square of the quantity 4 minus 2 square root of 5. We can expand this binomial here to be 4 minus 2 square root of 5 times 4 minus 2 square root of 5. And then we will do the long multiplication. Start with 4 times 4 is 16, and then 4 times negative 2 square root of 5. We will get this 8 square root of 5. Next, the negative 2 square root of 5 times 4. We will get this negative 8 square root of 5. And then negative 2 square root of 5 times negative 2 square root of 5. We will get this 4 square root of 25. And then we will simplify this square root of 25 to be 5. in the second term and the third term, we can see that they are the same radical. It means we have radicals of the same index and the same radicand. In that case, we can combine these two radicals in the middle. So in the third line, we have this 16 here, and then combining these two terms, we have this negative 16 square root of 5, and then plus the product of 4 and 5 is 20. So we can now add the 16 and the 20, it becomes 36. Then we simply copy this negative 16 square root of 5. So this is our final answer. There is another solution using a special product formula. So what I will do, I'm going to solve this same problem using the special product. First, I'm going to clear the board and then put the final answer on this side, the 36 minus 16 square root of 5. And I'm going to use the special product, the square of difference of two terms. In the answer, we will have three terms. So it means the x minus y quantity square is equal to these three terms, x squared minus 2xy plus y squared. So for the answer here, I am putting here three blanks to represent the three terms for the final answer. The first blank here is for this 4, I copied here and I put the power 2. Then for the second blank, I put these two terms here, the 4, and also this negative 2 square root of 5. So you see here the 2 square root of 5, the negative sign is already here. And then this number 2 here is a constant that we should always place. And the third blank is for this term negative 2 square root of 5, and we will put the power 2. So we were able to place all the necessary values. So we will now to simplify. The 4 squared becomes 16, and then minus. Then the product of these three terms, 2 times 4 times 2 square root of 5, we will get the 16 square root of 5. And then plus, we're going to square this term. Because of the square, the negative sign will go away. The 2 here becomes 4, and the square root of 5 is squared. The radical sign is cancelled with the power 2, so we'll have the 5 only that will come here. Then we will simplify, the 16 comes down, then minus 16 square root of 5, multiplying 4 and 5 becomes 20. Then we will combine the 16 and 20. So this answer here is the same with our answer a while ago when we solved this using the long method of multiplication. We're going to study how to rationalize the denominator. Rationalizing the denominator is the process of converting a fraction with a radical in the denominator to an equivalent fraction whose denominator is an integer. Let's have example 1. Rationalize the fraction 3 over the square root of 6x. In here, we're going to use the property when we have the nth root of a and this radical is squared. This is simplified into a. So let's go to our problem here. The step is we're going to multiply this by a value equal to 1. So we know that any number multiplied by 1 will not change the value of the original expression. The next is we're going to show that this one is a fraction. Please remember that our goal here is to remove this radical in this denominator. So there is a clue that we will multiply the square root by itself. It means in this denominator, we're going to use that same value of the square root of 6x. And for the numerator, we're going to copy that same denominator. So this is square root of 6x over the square root of 6x is a value that is equal to 1. Then let us proceed. We're going to multiply this 3 by this square root of 6x. We'll just combine them here. And multiplying this square root of 6x by itself, we will get this value, the square of this quantity, square root of 6x. And then on the next step, we can now use the idea of this property. We can now cancel that square root and the power 2. So this is now 6x in the denominator. In the numerator, we'll just copy that same value, 3 square root of 6x. But we can see here that the numbers 3 and the 6 can still be simplified. We can cancel the 3 and the 6. So the 3 becomes 1, the 6 becomes 2. So in the denominator, it becomes 2x. In the numerator, it is 1, but that number 1, we will not write it anymore. So only the square root of 6x comes here. So our final answer, the square root of 6x over 2x. Let's have example 2. Rationalize the fraction 5 over the binomial 2 minus the square root of 3. So for this binomial, our aim is to remove the radical in the denominator. We're going to use the product of conjugate pattern. What does it mean? When we have the x plus y multiplied by the x minus y, these two binomials here are conjugate of one another. To explain further, the conjugate of x plus y is the x minus y and vice versa. And this is one of our special product that when we multiply, the answer will be the square of the first term, then minus the square of the second term. So let us proceed with our solution. Our first step is to show that we are going to multiply this fraction by a value equal to 1. And this value equal to 1 is a fraction. And then we're going to think of our numerator and denominator here. For the denominator, we're going to multiply this value by its conjugate. We simply copy that same first term 2. We copy that second term, the square root of 3. But the minus here, we're going to put the opposite sign, plus. In some problems, it may happen that this is positive, so you must write negative. The next is the numerator. We'll just simply copy the conjugate value. So when this numerator and denominator are equal, this value is equal to 1. So it's not changing the value of our original fraction. The next is, we're going to multiply now the numerator by numerator, denominator by denominator. In the numerator, the number 5 is multiplied to the binomial. We'll just put them together. The 5 times the 2 plus the square root of 3. In the denominator, we're going to apply now our special product. So the first term 2 is now copied and then raised to 2. then minus. The square root of 3 is copied and also raised to 2. In the next line, we're going to simplify our denominator. So it means the numerator we simply copy here. In the denominator, the 2 square becomes 4 and then minus. The radical will be cancelled along with that power 2. Only the radicand 3 will come down here. So this is 4 minus 3. So when we simplify further, the 4 minus 3 becomes 1. And the same denominator is here. And for the final answer, we simply remove that denominator 1. So this is our final answer. Example 3. Rationalize square root of x plus square root of 7 all over square root of x minus square root of 7. In our rule, we're going to multiply this fraction by a fraction whose numerator and denominator is the conjugate of the denominator of the original problem. So we see that our denominator is square root of x minus square root of 7, and the conjugate is square root of x plus square root of 7. And this value of conjugate we copy in the numerator. Now we multiply the fractions. Numerator multiplied to numerator, denominator times denominator. In the numerator, we simply combine the two numerators. They are equal actually, and we can write this in exponent. So we have the square of square root of x plus square root of 7. In the denominator, we apply our special product. The first term is the square of square root of x minus the second term, the square of the square root of 7. Then we simplify the denominator. We cancel the radical and the power 2. Then we simplify further the denominator, and that is x minus 7. And in the numerator, we simply copy the same value. This is now the final answer. Today we're going to study how to solve a radical equation. First, let us define radical equation. An equation in which a variable is in the radicand of a radical expression is called a radical equation. How to solve a radical equation? There are 3 steps that we will follow. The step 1 is isolate the radical on one side of the equation. Step 2, raise both sides of the equation to the power of the index. And step 3, solve the new equation. Let us have example 1. Solve this equation. The square root of the quantity 5x minus 4 and then minus 9 equals 0. In step 1, it says let us isolate the radical on one side of the equation. So let us isolate this big radical. We want this negative 9 to be deleted. So what we'll do is to add 9 to both sides of the equation. So we can cancel the negative 9 and the positive 9 on this left side. And on the right side, 0 plus 9 will only be 0. So on the left side, the radical is now isolated. We'll go to the step 2. Raise both sides of the equation to the power of the index. In our radical, our index here is 2. So we are going to raise both sides of the equation by 2. We can now cancel the radical and the power 2 here. The 5x minus 4 will be simplified, and on the right side the 9 square is equal to 81. From here we'll go to the step 3. Solve the new equation. We're going to solve for x. We're going to add 4 to both sides of the equation. On the left side, the negative 4 will be cancelled out, and on the right side, the plus 4 will be reflected. Now we have 5x equals 85. And we want to get the value of x. Let us divide both sides by 5. So then we can now cancel the 5 and the 5. The x will come down here. And the 85 divided by 5 is 17. So this is our final answer. Let's have example 2. Solve the equation, the cube root of the quantity 5x plus 1, then plus 8 equals 4. Let's have the step 1 to isolate the radical on one side. So we have a big radical here, and then plus 8. We want this positive 8 to be out, so we're going to add negative 8 to both sides. In effect, the positive 8 on the left side of the equation will be deleted, and on the right side, the negative 8 is reflected. So let us simplify this into negative 4. Now we are able to isolate our big radical on the left side. We'll go now to our step 2 to raise both sides of the equation to the power of the index. Our index here is 3. So we're going to raise both sides by a power of 3. Then cancel the big radical sign along with that power 3. Only the 5x plus 1 comes down here. And on the right side, the negative 4 cubed is simplified into negative 64. So we're going to solve for the new equation, solving for x now. The positive 1, we're going to transpose on the other side. So the negative 1 is there. Or we say we add negative 1 to both sides. On the left side, the positive 1 here cancels out. On the right side, the negative 1 is reflected. Then we simplify this negative 64 minus 1. We have this negative 65. And then we're going to divide both sides by 5 so that we will isolate the x. So when we cancel the 5 and the 5 on the left side, only x comes down. Then the negative 65 divided by 5 is negative 13. So this is our final answer. So let us go to example 3. Solve the equation. Step 1. Isolate the radical on one side of the equation. In here, the radical is isolated already, so we will jump into the step 2. We're going to raise both sides of the equation to the power of the index. The index here is 4, so we're going to raise both sides of the equation by power 4. So the fourth root of the quantity 5x minus 4 is now raised to 4, and on the right side the 1 is raised to 4. And then on the left side we can cancel now the big radical sign along with that exponent 4. The radicand 5x minus 4 comes down here. On the right side, the 1 raised to 4 is equal to 1. Then we will go to step 3 to solve the new equation. Means we're going to solve for x. The negative 4 should be cancelled out by adding 4 to both sides. So adding 4 on the left side will cancel the negative 4. On the right side, when we add 4, it will be reflected here. So 1 plus 4, and then simplifying the 1 plus 4, we'll have the 5, and then we're going to divide the equation by the coefficient of x, which is 5. So 5x over 5 is equal to 5 over 5. So we cancel this 5 and 5. Only x will come down here. On the right side, 5 divided by 5 equals 1. So this is our final answer. Let us have more sample problems. Problem 1. Simplify the following. We have here three expressions. Let's begin with A. Negative of the square root of 81. In the radicand, 81 can be shown as 9 square. And by the rule, the power 2 with the index 2 can cancel each other. Finally, the answer here is negative 9. Expression B. The fifth root of negative 32. In the radicand, this negative 32 can be expressed as the negative 2 that is raised to power 5. This power 5 now, and the radical with the index 5 will cancel each other. So negative 2 is the final answer. Expression C. The fourth root of 16x raised to 8. Let us express these expressions or these numbers into a power of 4. For 16, this is equal to 2 raised to 4. For the x raised to 8, we can rewrite this as x squared that is raised to 4. Then we combine these terms with power 4. So that will be 2x squared that is raised to power 4. We have now here a monomial that is raised to power 4. And this power 4 and the radical with index 4 will cancel each other. Finally, the answer is 2x squared. Problem 2. Write 2x raised to 5y squared all raised to 1/2 as a radical expression. The denominator of the rational exponent will be the index of the radical. The denominator here is 2. So we can write like this. The square root of 2x raised to 5y squared. But we know that with the index 2, we can simply cancel it out. So this is the final answer. Problem 3. Write the fourth root of this quantity, the square of the fraction 2xy all over 5z. The index of the radical becomes the denominator, that is 4, of the rational exponent, while the exponent of the radicand, which is 2, becomes its numerator. So we can write like this. 2 over 4, that is the power of the fraction 2xy over 5z. But in here we see that the 2 over 4 can be simplified into lowest term. So it becomes 1 over 2 of the same fraction. Problem 4. Use quotient property to simplify. The square root of the fraction 28p raised to 7 all over q squared. By quotient property, we distribute the square root to the numerator and denominator respectively, just like this. And we can see that in the denominator, the square root of q squared can be simplified into a simple q, while in the numerator, we're going to show this 28 as factors such that one of the factors must be a perfect square number. So 28 becomes 4 times 7. For the p raised to 7, we're going to split this into two factors such that one of the factors must be a perfect square number. So we have p raised to 6 times p. Now let us show the perfect square numbers with a square form. For the number 4, we can write as 2 square. For this p raised to 6, we can write as p cubed, that is raised to power 2. And from here, we combine those terms with power 2. So this number 2 and the p cube will come together as 1. Then we put together the 7p in the front. By multiplication power, we can distribute this radical into the square root of 7p times the square root of the square of 2p cubed all over q. And this expression we can simplify. We can cancel the power 2 with the radical with index 2. Now the 2p cubed will come in the front times the square root of 7p all over q. Problem 5. Perform the operation. We have here two expressions. Let's begin with problem A. The square root of 48 plus the square root of 27. We know that in adding or subtracting radicals, the index must be same, also the radicands. In here, the radicands are different. One is 48, the other is 27. And 48 is not a perfect square number. Same is true with 27. We're going to factor now these two numbers in such that one of the factors must be a perfect square number. For this 48, we factor this out as 16 times 3. For the 27, the factors are 9 times 3. Then we show 16 as a perfect square number to be 4 square. For the 9, we write as 3 square. Then we can simplify the radical. This 4 square, we can put this 4 outside the radical symbol. So it becomes 4 square root of 3 plus this 3 square, and the number 3 comes out, so 3 square root of 3. Now we have a radical with the same index and the same radicand. In that case, we're going to combine the numerical coefficients of the radicals respectively. So we have 4 plus 3, that is 7, and we copy that same radical, the square root of 3. Problem B. Cube root of 24 minus the cube root of 81. The radicands are not equal. Also, the radicands are not perfect cube number. So we're going to factor out 24 and 81 respectively, such that one of the factors must be a perfect cube number. For 24, it becomes 8 times 3. For 81, it becomes 27 times 3. Then we show these numbers as a perfect cube numbers. The 8 becomes 2 cube, and the 27 becomes 3 cube. Then we can simplify this radical. We can move this base 2 outside the radical symbol. So we have 2 cube root of 3 minus, in here, this base 3 we can put outside the radical. Here comes the 3 times the cube root of 3. Now we can subtract radicals with the same index and the same radicand. We will operate only on the numerical coefficients. So this will be 2 minus 3. That is negative 1. Or simply we write negative of the cube root of 3. Problem 6. Perform the operation, letter A, square root of 7 times the quantity 5 plus 2 square root of 7. Here we're going to distribute this square root of 7 to each of the terms inside the grouping symbol. Let's begin with square root of 7 times 5. The answer is 5 square root of 7. Then we multiply square root of 7 by positive 2 square root of 7. We will have plus 2 square root of 7 square. From here we can simplify this square root of 7 square. We cancel the power 2 with this radical. So the number 7 comes out to be multiplied with the number 2. 2 times 7 is 14. By convention, we write the whole number in the front. So we have 14 plus 5 square root of 7. Problem B. 3 minus 2 square root of 7 times the quantity 5 minus 4 square root of 7. We're going to use here the distributive property. We multiply this 3 to the terms of the other group. So let's begin with 3 times 5. That is 15. Then 3 times the negative 4 square root of 7. And that is negative 12 square root of 7. Then we take this negative 2 square root of 7 multiplied by 5. So we have negative 10 square root of 7. Then negative 2 square root of 7 times the negative 4 square root of 7. We have positive 8 square root of 7 square. Let us now simplify further. For this 15, we will copy down there, and we are going to combine these two terms, negative 12 square root of 7 minus 10 square root of 7. We will get negative 22 square root of 7 plus this 8 square root of 7 square. We can simplify this power 2 with the radical will cancel out. 7 will come down to be multiplied with 8. The product is 56. Then we combine 56 by 15. It becomes 71. Then minus 22 square root of 7. This is the final answer. Problem 7. Perform the operation. The square of the quantity 2 minus 5 square root of 3. Remember that we have a special product like this. The square of x minus y equals x squared minus 2xy plus y squared. We are going to apply this special product to our problem here. So this 2 minus 5 square root of 3 raised to power 2 becomes 2 squared minus 2 times 5 square root of 3 plus the square of 5 square root of 3. Let us simplify now. 2 squared is 4 minus, we multiply 2 by 5. That is 20 square root of 3 plus this power 2 we distribute to 5 and to the square root of 3. So here we have 5 squared times the square of square root of 3. Then we simplify. 5 squared becomes 25 times the square root of 3 cancels this power 2 and the radical. Only 3 comes down. So 3 times 25. That will be 75 added to 4. That is 79 minus this 20 square root of 3. Problem 8. Rationalize the denominator. We have two expressions here. Let's begin with A. 10 over square root of 6. Considering the index here, and that is 2, we need a power 2 to cancel this radical. So we multiply this denominator, the square root of 6, into square root of 6 also. And this denominator value we copy in the numerator. That means our original problem, 10 over square root of 6 times square root of 6 over the square root of 6. So we multiply the fractions. Numerator times numerator becomes 10 square root of 6 over denominator times denominator will give us square root of 6 square. We know that the power 2 and the radical with index 2 will cancel each other. only this 6 will come out. So we have 10 square root of 6 all over 6. But the 10 over 6 can still be reduced to lowest term. By dividing two of these numbers, 10 becomes 5 and 6 becomes 3. Finally, the answer is 5 square root of 6 all over 3. Letter B, the square root of the fraction 4 over 27. By quotient property, we can distribute the radical to numerator and denominator, just like this. We can simplify this square root of 4 to be 2 over the square root of 27. Now we want to rationalize the denominator. With the index 2, we need a power 2 to cancel this radical. So we multiply this square root of 27 by itself, another square root of 27, and we copy this value in the numerator. So we multiply 2 over square root of 27 times square root of 27 over square root of 27. We multiply now these fractions. 2 times the square root of 27, we just put them together. In the denominator, it becomes the square root of 27 with power 2. So we can cancel the power 2 and the radical. So it becomes like this. Finally, 2 square root of 27 over 27. Problem 9. Rationalize the denominator. Expression A. 8 over 1 minus square root of 5. We can see here that we have two terms in the denominator, one with radicals. So we're going to use here the idea of conjugate. Remember our special product x minus y times x plus y. These two expressions are conjugate of each other. And when we multiply, the special product is x squared minus y squared. That means this 1 minus square root of 5, we're going to multiply this by its conjugate. And that will be 1 plus the square root of 5. And this value of conjugate, we simply copy in the numerator. Now we multiply the fractions. Numerator times numerator, we put them together. In the denominator, we apply our special product. So this is now 1 square minus the square of the square root of 5. Then we simplify the denominator. 1 square is 1 minus the square of the square root of 5 is simply 5. And 1 minus 5 is negative 4. We can simplify this 8 by negative 4. This negative 4 becomes negative 1 and this 8 becomes 2. Finally, we have negative 2 times the quantity 1 plus the square root of 5. Problem B, square root of x plus square root of 8 over square root of x minus square root of 8. In this case, again, we use the conjugate idea. Considering our denominator, this is negative, so the conjugate should be positive. Square root of x plus the square root of 8. And this conjugate value we copy in the numerator. Now we multiply the fractions. Numerator times numerator becomes the square of the quantity square root of x plus square root of 8 all over. In the denominator, we apply our special product. So this is the square of the square root of x minus the square of the square root of 8. Whereas we can simplify, we cancel the power 2 with the radical also in here. So finally, we have this final answer, x minus 8 in the denominator, same in our numerator. Problem 10. Solve 2 times the square root of the quantity 5x plus 1. And then minus 8 equals 0. The rule says in step 1, let us isolate the radical. First, this negative 8 we transpose to the right. It becomes positive, just like this. And then, this coefficient 2 of the radical, we are going to eliminate. Let's divide this equation by the same value 2. In that case, this number 2 comes to the right side as denominator. So 8 over 2 is simply 4. We are done with step 1. The radical is now isolated. For step 2, we raise this equation into a power equal to the index. Our radical here has no index. That means the index is 2. So we raise this equation by the power 2. And this power 2 will come to the left side and to the right side of the equation. Let us now simplify the left side. The power 2 and the radical with index 2 will cancel each other. That means we simply copy 5x plus 1 down here equals the right side, that is 4 squared, that is 16. Let us now solve for x. This plus 1 we transpose to the right becomes negative 1. 16 minus 1 is 15. Then divide this equation by 5. So x equals 15 over 5. Finally, x equals 3.